So, last class we have discussed the what is called the dynamic programming of a discrete time system using principle of optimality. We have described the basic principle behind this, and also we have taken one example which we could not complete during that time during last class. So, let us recap the example and complete this example now. So, our problem is given the discrete time system, it is a first order difference equation. Initial state x of 0 is equal to 8 is given. Our problem is minimize this performance index, the standard performance index, and it is in quadratic form, and this is the terminal cost is given. So, our problem is using the principle of optimality find control sequences u 0, u 1, assuming there is no constant on the control signal u of k. So, we will start what is called principle of optimality principle we will apply, that means from we will start from the backward pass. We start with the backward pass. So, if you recollect this one, that our terminal cost is that one. So, from x 2 to we will move with x of 1 state, and for that one what should be our control sequence u of 1 we have to find out. So, j of 1 performance cost when you will move from j 2 to j 1, what is the performance cost? That minimize this performance index, and that is we are writing from this expression. If you see n is equal to j is equal to 1, then x of phi of 1 phi of n x of then, that is the terminal cost, we know this one. Now, n is equal to that is 0 1 k 0 to 1. So, k is equal to 1, then this means 2 x of 1 whole square 4 u 1 of whole square. That means, we are moving from the terminal cost j 2 to j 1. So, that is why we have written it into this form. So, what is that from j 2, this is the terminal cost at j 2. Now, we are moving with the j 1, j 2 plus j 1 total cost. So, this is the expression. Now, this x 2 we can write it in terms of x 1 from the dynamic equation, dynamic discrete time equation given to this. So, that x 2 is now replaced by this expression, and this remaining is same. Now, you see here that minimization of this performance index depends on the x 1, agree, because we have to minimize this and use selecting the u of 1, and we have also seen there is no constant imposed on control input u of 1. So, that means, so if you see this one, then our optimal u is the function of x 1. From the previous slide you see is a function of x 1 only. So, it is nothing but a problem of optimization problems. So, partial differentiation of u of 1 with respect to this function cost function with respect to u of 1. So, if you do this one, the u is involved in u of 1 involved here and in this expression. So, this will come with this expression. Ultimately, we got u 1 in terms of x 1 is this. So, x 1 again you see I cannot find out u of 1 until unless I know x 1, but I know x 0. So, x of 1 can be expressed in terms of x 0 and u 0, where u 0 is unknown, but x 0 is known to us known to us. So, if you use this expression into that j 1 expression, that is this, and you know x 1 this and u 2 in terms of x 1 I have written this one, and j 2 expression is nothing but a x 2 minus 20 whole square, and x 2 is replaced by that one. So, now it is that terminal cost required from j 2 to j 1, what is the cost is involved with this one. So, now this if you can simplify, ultimately it will boils down to these expressions, this after simplification. So, next we will go from j 1 to j 0, that means what is the cost for moving the backward pass from j 2 to j 1, total cost. So, it is not a j 1, this is j 0 and it is a function of x 0. So, if you see this one, so this now you say I will write this expression of j 1 here. So, u of 0, then half twice x square 0 plus 4 u 0 square plus j 1, and j 1 just now we got it this expression, and here we will express x 1 in terms of x 0 and u 0. Wherever x 1 is there, we replace by x 0 and in terms of x 0 and u 0 from the dynamic equation of discrete time systems. So, this expression if you see that first expression is x 1 square. So, x 1 square is nothing but a 4 x 0 minus 6 u 0 whole square. Agree? Because you see this our basic expression for dynamic equation, when that k is equal to 0, this x of 1 is equal to 4 x 0 minus 6 u 0. What I have written it here in place of x 1 square, I have written that one. Then 2 plus see this one, that expression z 2 into 12 into x 1. So, I will replace x 1 by x 0, 2 into 12 into x 1 means 4 x 0 minus 6 u 0. This is 4 x 1 minus 60 divided by 19, that whole square. The next term is like this way, 4, if you see this one, 4 x 1 minus 20 divided by 19 whole square, 4 x 1 is here 4 x 0 minus 6 u 0 divided by this 4 minus 20 divided by 19 whole square. Agree? So, this and that equal to 0, this one. So, we have to write here, this is the mean, okay, this 0 we will write it here. So, del j divided by del u of 0, that one, this whole expression, that half twice x 0 square plus 4 u square 0 bracket close plus 4 x of 0 minus 6 u of 0 whole square. Because this is the performance index, this performance index we have to use, you have to minimize using the proper choice of u 0. So, you have to differentiate gradient of this with respect to u 0. I am finding out this is a capital u 0. You write if it is small, because we have considered small, because it is scalar input u of 0 small. So, this plus twice into 12 into 4 x of 0 minus 6 u of 0 minus 60 divided by 19 bracket, that whole thing square plus 4 into 4 x 0. This same expression I am writing minus 6 u 0 minus 20 divided by 19 whole square. This 4 into x 1, 4 into x 1 minus 20. So, 4 into x 1, 4 into x 1, this multiplied by this whole thing is your 4 x, 4 into this whole thing is x 1 minus 20 divided by 90 whole square is equal to 0. So, if you simplify this one, differentiate this with respect to u term is involved here, 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 in all terms except the first term of this one. So, if you do this one, then we will get it that 4 u 0, just you differentiate that this is u square 2 to cancel 4 u 0. So, you just check it this one 2 into 4 x 0 minus 6 u 0 whole star minus 6. From the first term of differentiation of this one, we will get twice this and differentiation of that quantity minus 6. So, twice into this, then plus twice 19 square, then bracket 2 star bracket 12 4 into x 0 minus 6 u 0 bracket close minus 60, then bracket close into minus 72. So, that you use this one. So, that plus the third this term differentiation, this we have done it, this we have done it. Now, this one, that 119 square, then 2 star bracket 4 into 4 x 0 minus 6 u of 0 minus 20 bracket close in star minus 24. This is simple what is called differentiation of that j 0 with respect to u of 0 is equal to 0. If you solve this one, because I can write it now u 0 in terms of x 0, and then since I know the initial state of x 0, I can easily calculate u of 0. So, using x of 0 is equal to 8 in the above equation, okay, we get u of 0 is equal to 4.81. Please check it, this calculation. Okay. So, we got it this one. We know u of 0 and we know x of 0, then immediately we can find out x of 1 by using what is called the dynamic state equation of the system, that means discrete time systems. So, basic equation of this one, if you recollect, this is x is equal to j is equal to 4 of x k minus 6 u of k, and x of 0 is equal to 8. So, immediately I can find out x of 1, k is equal to 0, if you put x of 1 is equal to 4 of x 0 minus 6 of u 0, and you know the value of x 0 u 0. So, 4 into 8 minus 6 into 4.81, whose values will come 3.14. So, in its state value you know it. Then then we can find out, next we can find out x of, so u of 1 we can find out. Look this expression u of 1 we calculated in the last class. If you see that u of 1 we have calculated in the last class, that u of 1 expression is nothing but a 12 of x of 1 minus 60 divided by 19. I will show you this one, that last class from equation 2 you can write it, that from 2 you can write it, from 2 we can write it. We know x of 1 now. So, this is nothing but a 12 x of 1, you got it just now, you got it 3.14 minus 60 divided by 19. So, that value will come your minus 1.175. Check this below. So, now so once you know u 1, you know x 1, immediately I can find out x of 2. Now, x of 2 is equal to 4 of x 1 minus 6 of u of 1 is equal to 4 of x 1. I know that x 1 value I got it 3.14 minus 6 into u 1 value is minus 1.175, that will come near about 19.61. So, and from starting with back pass, we have found out the trajectory of x 0, x 1, x 2, and simultaneously we are getting the control, optimal control sequence of u 0, u 1. Okay. So, which completes the forward pass. So, first we have done backward pass, then once we complete the backward pass, that means J 2, because terminal cost n is equal to 2 is J 2, you got it, we have no terminal cost from J 2 to J 1 we found out by selecting the optimal choice of u of 1. Then from J 1 to J 0 we found out by proper selection of, means in other words it is a optimal selection of u of 0. Once you completed the backward pass, then we have to do the forward pass, which completes like this way, finding out x 1, x 2, then u 1, then x 2. In this way we found it. So, this is the complete solution of the problem which we have discussed last class. So, now we will consider a new topics which is called time optimal minimum time control problem of a linear time invariant systems, linear time invariant system. By the name itself, that this statement of the problem is like, they are given the system dynamic equation, our job is to find out the control sequence, agree, in such a way so that we can reach from our initial state to final state within a minimum time. Agree? So, let us state this one, consider the linear time invariant systems, linear system time invariant system described by x dot O is equal to a of x t plus b u of t, and our initial state is given, x to 0 is given, you can given. So, let us assume that our input, number of inputs is m and number of states is n, and immediately we can find out the dimension of a matrix, system matrix, and input matrix dimension, immediately we can find out. So, our job is to transfer the state x of 0 to a final state x at t is equal to T f is xf, transform this with the sequence of control with the optimal control law in a minimum time, that is all. Before that, we made an assumption first assumption the system must be is completely controllable. That the rank of B A B A square B dot dot A n minus 1 B is equal to n, where n is the dimension of the system, or state vector dimension. So, this is the first assumption, this the system must be completely controllable. Then second assumption is made, admissible control, means the input must be satisfy the following constraints, in the sense input is now constant. So far we have discussed, we have not made any constraint on the input when we did the optimal problem solution by using calculus of variation. We have not made any constraint on the inputs as well as on the states. Here we will just first consider there is a constraint on the input. If you see the physical point of view, that control effort or control signal, we cannot apply whatever is coming from the controller output, that we cannot directly apply to the systems, because all physical system has a limitation of control signal input. So, you have to restrict it. So, you have to constrain the control input signal which is coming from the controller, we have to restrict it in general. So, so in general it is saturation element is used it here. Here we are telling admissible control, the control inputs, must satisfy the following constraint. So, what is the constraints are imposed on the input controller, that u of t, what is the control input is coming from the controller or from the design of the controller, that must be restricted with a u min of t or less than equal to u max of t, or in other words you can say, if the u min value lower limit and upper limit are same, suppose this u max is 5 volt, agree, and u minimum is also 5 volt, then in that sense I can write it u of t, the each component of u mod must be less than equal to alpha I magnitude, where I is equal to 1 2 dot dot m for all t. Suppose we have considered input magnitude in upper bound is 10 volt and lower bound is minus 10 volt, then I can write it absolute value of this is equal to less than alpha I is 10 volt. So, different control inputs, that upper bound and upper bound agree and lower bound if are same, that alpha I may be different. Suppose control one input upper and lower bound, if both are same in negative sign with the then it will be a 10 volt, u 2 may be 5 volt, all these things. So, this is the thing. Say alpha I you have restricted to 1, that upper value of the control input is positive 1 volt and lower bound of the control input for I is equal to u I is equal to 1 is equal to, let us call, minus 1 volt. For all cases it is plus minus 1 volt. So, problem statement, though we have explained problem statement, now we are writing the statement of the problem statement. So, it is desired to apply an optimal control input u star of t that satisfies the constraints u of I of t less than equal to 1. You can say I is equal to 1 to dot dot m, since m is the number of real. For all cases with the limit restriction we made it same, and drives the system x dot is equal to a x t plus b u of t, drive the system from initial condition or initial state, from initial state x t 0 is equal to x of 0 to the desired state, desired final state x t f is equal to x f in minimum time. In other words, our optimization performance index optimization problem is optimization problem is described with a performance index P I. In otherwise, minimize the performance index, this T 0 to T f 1 into d t is equal to T f minus T 0. If T 0 is 0, minimize that one T f. Agree? That is our problem. Now, you see this one, that this problem, our integrand of the performance index is 1, is not a function of u. So, in other words, you can say our problem is like this way. So, our initial state x of t 0 is equal to x 0, and we have to find out the optimal path such that the performance index is minimized, in the sense that state x of t 0 x 0 will transfer with the optimal control signal to a desired state x t f is equal to x f in a minimum time. Let us call this is the optimal path in a minimum time. That is our problem. So, we shall call such a controller is minimum time control problem. Agree? if the final state is terminating is at origin, then this problem is called the optimal time regulator problem. If note, when xtf is equal to 0 means at the at the origin of the state, origin comma, we will be dealing with time optimal regulator problem or regulator systems. So, now how to solve this one? If you recollect our earlier problem, that in optimization problems we have given the description of the systems, then we have given a performance index of the corresponding performance index. Our problem was to solve the u, to find out the optimal control law u of t such that this performance index is minimized. So, we have used the technique calculus of variation to solve this problem. Please recall all the steps what we have considered earlier. That means, first we have considered that find a what is called Hamiltonian functions, agree, but in that problem we have not considered any constraint, that u was unconstrained, state also unconstrained, but here now our problem is coming constraint on u. Then how to solve this one? Basically, the procedure is similar to that one only, just one step we have to see very carefully, which is different from other earlier procedure. So, first we will defining the Hamiltonian function, Hamiltonian function. So, what is the Hamiltonian function? If you recollect that our performance index is there, agree. So, we form the Hamiltonian function by taking the integrand part of the performance index. Here, if you see, our integrand part of the performance index is 1. So, our Hamiltonian function is h is equal to h function of 1, that integrand part of the performance index 1 plus the co-state vector lambda transpose this, and that is function, that is next is corresponding to our problem is a of x t plus b of u t, and in general it is the dynamic equation right hand side of the dynamic x dot is equal to a x plus b u, co-state vector transpose multiplied by that right hand side of the dynamic equation of the systems. This is our Hamiltonian function, h function, Hamiltonian function, agree. And this part, first part in our case is the integrand part of the performance index. In this case, since it is a time optimal problem, the integrand part of this performance index is 1. So, and other we will follow the procedure that once we form the Hamiltonian function. So, let us call this is the equation number 1. Agree? So, the resulting, now I can write the resulting condition for optimality can be derived similar to earlier case, can be derived using calculus of variations. So, what is our calculus of if you see x dot is equal to del h del lambda of t is equal to our x dot state vector, which is nothing but a x of t plus b u of t, that we have derived earlier if you see this one. So, let us call this is the equation number 2. Then co-state vector we can write, this is the state equation, co-state vector we can write it del h del x of t is equal to lambda minus lambda dot of t is equal to lambda dot of t is equal to, now if you see the del h, so we have differentiation this is nothing but a transpose lambda of t minus. Okay. So, this is the co-state equation. So, let us call this is equation 3. So, now if you solve this one if you solve this one, then you can find out this so, lambda of t is equal to, from this one equal to e to the power of minus a t of t lambda of 0. Agree? So, now this is the co-state vector equation solution, you know it, that one. So, now we can write it that another is delta h. Now, look at this one, this is more important, del h del u of t is equal to 0. Then what we can write it from this, you see del h del u. So, it is nothing but a b transpose your lambda. So, that is equal to b transpose of lambda is equal to 0. Agree? B transpose lambda is equal to 0. So, now you see this does not contain u. So, we cannot find out that one, but why it is does not contain u? Because our in the what is called in the Hamiltonian function is a linear function in u, there is no quadratic function of u. Agree? So, this we cannot handle like this way. So, this does not, you can write this does not involve u of t, because h is a linear function of u, because h is you see this one, when you differentiate this one, that will be a plus, not this one. Agree? Please change this one, that my lambda, this is the co-state vector equation. Now, I am differentiating with respect to x, so that will be a transpose of this. So, the solution of this one is that lambda t solution is this one, a simple state equation solution is this one. So, because h of t is linear in u of t. So, it clearly indicates to minimize u of t, no sorry, h of t, clearly minimize h of t. Now, you see, to clearly minimize u of t, you have to select u of t. Clearly minimize h of t, you have to select u of t such that the function is minimum. So, clearly to minimize h of t, h of that function Hamiltonian function, agree, select u of t to make lambda transpose t be u of t, that part, lambda transpose b u of t, lambda transpose b u of t, select u of t to make this as small as possible. So, that is our requirement. So, this is called Pontryagin minimum principle. So, so we have to choose, we have to minimize h, because we cannot minimize h this one by selecting u, because there is no function of this delta is, there is no u terms is involved, because of that what is called Hamiltonian function is a linear function, not a quadratic function or a nonlinear function. That is why you will not be able to do. So, what we have to do? We have to use the minimum Pontryagin minimum principle here. So, in order to minimize this, select u, so that this should be as small as possible. So, naturally so this, it may be noted that the control signal u of t affects h only through tell me this expression, if you see this one, that the control u affects h, control u affects h only through this term lambda transpose b u t. So, only through the term lambda of t transpose b u of t, which equal to lambda. Just now we have find out the solution of lambda of this one. You see lambda of this transpose of this lambda 0 transpose, if you take transpose both sides lambda 0 transpose. So, this is equal to lambda 0 transpose e to the power of minus a t b u of t, agree. So, the important is the Pontryagin minimum principle that PMP states that Hamiltonian function h of dot should be minimized by over all possible control input, over all possible control input. So, what does it mean? this permits including the constant. You see h, which is a function of, if you see x of t, then u of t, then lambda of t and t. So, you find out the optimal control law, use stars. The star indicates the optimal, what is called quantities, optimal quantities. This is not star. So, less than equal to h x star of t, then u of t, that lambda star of t, then t. For all permissible input, that means u of t belongs to u of a. A stands for all permissible, admissible control, A for admissible control. U A, this indicates U A admissible control. That means, the control input is restricted with this constant, with this one. Agree? So, this for all time t belongs to that 0 to t f. If t 0, this is our t 0. If t 0 is 0, then 0 to t f, or if it is not 0, t 0 to t f. Agree? So, what is our equation? We have given it 3. Let us call lambda is equal to this, equal to our equation number 4. The co-state equation, co-state vector equation is 4. Then we have written that what is called the Hamiltonian function. We have defined a Hamiltonian function is here. Agree? So, this, let us call this equation is equation number 5. Agree? So, now note what is the corresponding our Hamiltonian function h of this is equal to 1 plus lambda transpose. Lambda transpose we have just noted in terms of initial lambda 0 transpose, then your e to the power of a t, then a of x t plus b u of t. Let us call this is equation number 6. Now, see this one lambda, what is our Hamiltonian matrix is considered, that is first is Hamiltonian matrix is considered, that we in place of lambda t I am writing it that quantity, and then remaining is as it is, remaining is as it is. So, this. So, now from this equation you see when this function will be minimum, that Hamiltonian function. So, this I am now writing into two parts, this into lambda transpose of 0 e to the power of a t into x of t plus lambda transpose of 0 e to the power of minus a t b u of t. So, we have a choice with u t now. Suppose this quantity is positive. So, this quantity is what? This vector is n by m, the dimension of B. This dimension is n cross n, and this dimension is 1 by 1 row and column. So, if you see is nothing but a, that is number 1 row m columns, 1 row m columns, and this dimension is m rows 1 column. So, this is a vector of this one. Agree? So, now I can write this will be minimum, that from 5 and 6, from 5 and 6 I can write it, from 5 and 6 we can write the each component of u, we can write u I of t star is equal to plus 1 when lambda transpose of 0 e to the power of a t and b I. What is I? B is a, if you see this one, B is a, how many rows are there? N rows, m columns. So, first column of B is B 1, second column of B is B 2 and ith column of B is B I. So, I am writing this when, and this will be what? This is a n row 1 column, n row 1 column, and this is n by n and this is 1 by n. So, this will be a scalar quantity this. So, if this absolute value of this one or this value is less than 0, each element of B I am considering, each element, this is you will, each element of u I am considering. If this quantity, because this is what, whole thing is a your, this whole thing is a row vector. So, first each element of this row vector, if it is a less than 0, then this should be a positive. Then product of this one, this means which one? The corresponding element of u must be positive. If this is negative, corresponding ith element of u, agree, must be positive. So, that is why I am writing this positive. Now, if lambda star of j e to the power of a t b I is greater than 0, this is scalar. If you see, this is scalar, this is also scalar, then it is this. So, ultimately that this function value will be reduced, minimized in this way. So, this, so u we have to switch either plus 1 or minus 1, agree, when this, when you have followed my this point, this quantity, if you see from here to here, I just from here to here, if you see this here to here, you have a one row, this like from here, n columns, this is the n columns, this is the n columns. And what is this? This one I am writing it u 1, u 2 in this way, m rows. So, ith row, let us call this is I, ith column of this multiplied by ith row, this is the ith column, this is the ith row of, it should be multiplied. So, ith column of e to the power 0 lambda transpose 0 e to the power of a t, ith column of that one, if it is a negative, then the ith row of u must be positive. If it is a positive, that must be negative and resultant will be always negative. So, that will be a function value will be minimum as possible. So, this, so we can make it what is called this one to up to infinity, but we have a restriction that input must be a plus minus 1, that one, that is why we have given this. So, in short, we can write both the equation, we can write combinedly, we can write it using the signum function as g n is equal to lambda transpose 0 e to the power of a t b I. So, which, because this is a scalar, we can write it this equal to minus S g n b transpose b I transpose e to the power of minus a transpose of t lambda of 0, which is nothing but a as g n b I transpose e to the power of minus a transpose t. This whole thing, sorry, this whole thing from here to here, this is nothing but a lambda of t. say the solution of lambda of t, we have just found out that from the co-state vector lambda t e to the power of a t lambda 0. So, e to the power of a t lambda 0 is lambda I. The signum function, if this quantity is greater than 0, agree, then that value is positive, it is switching to the positive. Since it is preceded with a minus sign, so there is a u I is negative. If this quantity is negative, then signum function of this one indicates it is a negative, 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 positive. So, it is a positive, u is positive. So, that is the our, we can write it this ultimately minus signum function of this one b I transpose lambda of t is, let us call equation number 7. So, the form of control. So, what we can write is the form of control defined by equation 7 is referred to as a bang control. Since the control is switching between the two limits, since the control switches between its limits. Agree? So, this is called the bang control. So, next class we will take in one simple example and explain you how this control action can be taken into consider for solving the what is called time optimum control problems. So, we will stop it here now.